You understand now? So, do you have any questions so far up to this point? I can clarify if you have any. All good? Because you have practiced it. I know.
Yes, where is some good websites or something that we can get practice questions from?
Oh, you mean the question?
Mm-hmm.
One is going to be your textbook.
Okay.
You're going to have the several questions for each subsection you have in the book. So this is going to be one place. Right? And the other going to be, of course, I'm going to put the practice question on Blackboard. You're going to do that. And then after that, homework going to be the other one.
Okay.
Right? So homework, just like it's not just completion. So if you do 3 or 4 trials there, you're going to have the answer, right? But make sure you know why this is the answer. So that's going to give you more idea. Okay. Okay. All right. So this is the last reaction you have in this chapter. So this is hydrogenation. So just by the title, you have the idea, right? So what is hydrogenation?
Addition of water.
Yeah, so you're gonna add hydrogen, right? So you're gonna adding that. And then here you have the catalytic. That means you're gonna use the catalyst for the reaction, right? So why you're gonna use the catalyst? Either the reaction is not favorable, or you're going to have very low yield in the reaction. So to increase the yield or the product you have, you're going to use catalyst sometime, right? So these are the two things. So before we go to the reaction, let me say why you're going to use this catalyst. If you see this particular reaction, so this one you will not have that in the question probably, you're going to have just the hydrogen. But this is just to know why you're going to need a catalyst. Okay? So you can calculate the entropy change. So you see the reactant there, you see the product, right? So what's going to be the change in entropy? You're going to do always product minus reactant numbers you have. So it's not number of atoms you have there. So the individual entity. It can be ion, can be molecule, right? If it is separate atom, yes, you're going to count that too. But not the atoms combined to make the molecule. You don't count separately. You're going to count the molecule as a whole, one entity, right? So, how many products you have over there? Only one, right? So, you have one product there. How many reactants you have? You have one over here, you have one over here. So, you're going to add that. So, you're going to have 2 reactant molecules. And then you're going to have the one product. So, delta S is going to be number of product minus reactant, right? So you're going to do 1 minus 2, which is minus 1. So the decrease in entropy is not favorable for the reaction, right? The second law says any process in the universe is going to occur to increase the entropy, right? So the change is going to be positive if it is favorable process. Right? That means the negative means probably it doesn't want to go to the product side. Right? So that's why you're going to use the catalyst that gonna increase the favorability by changing the profile of the reaction. Right? So the other thing is, if you see the heat of reaction, so you have the negative 29, that's the value, right? But it is favorable. Whenever you have the negative delta H, what that means? That means, so it doesn't say anything about the barrier height of the reaction. What it says is, you have the reactant over here, you're going to have the product somewhere over here. That's what it says. We have no idea about the profile. That's the kinetics. Okay? So just the thermodynamics or delta H going to say either you're going to have the delta H negative or positive. If it is positive, you're going to have the product above the reactant. If it is negative, you're going to have the product below the reactant, right? So that means the product is more stable, right? So here you have the contradiction, right? The thermodynamics says that the product is more stable, right? So you're going to have the more stable product over here. This is stable. Then the reactant, right? So the reaction should be easy to carry out based on this. So the process once to go to the product side just by looking at the energy of the product. But the entropy says that it doesn't want to go there. Right? So you have the two contradicting facts over there. So that means you have something over here, that's the kinetic part that we don't know. That is going to control. Once the barrier crosses, the product going to be more stable, want to be there. So you have something that's going to make it harder to cross the barrier, right? So what that can be? So that can be like this, right? So probably you're going to have the very high barrier there. So not all the reactants are going to cross that. So you don't have the product, even if it is favored. Okay? So if you use the catalyst on that, so what it's going to do is it's going to lower the barrier. That's the function of the catalyst. You can call the mechanism. So it's going to alter the path to go from reactant into the product by making it easier. When you have that, you're going to have the product, less energy, so you're going to be more stable, right? That's the reason why you're going to see the catalytic in the title. Okay, so you're going to use the catalyst. So that's what you're going to do. So we're going to lower the energy of activation. So the reason for the less yield without the catalyst was the high barrier, energy of activation. That was the reason. So catalyst gonna lower that, and you're gonna have the power. Okay. So now, what catalyst you're gonna use for that? So you can use any metal surface. So the idea over here is you're gonna have the back-end orbitals in metal, in particular the metals that have the D and higher orbitals. It's not like sodium, calcium, magnesium, not that type of metal. You're gonna have just the S and P orbital over there, right? So you're gonna go to the transition metal. So they're gonna have the D and above orbitals. So palladium, platinum, right? So even iron, you can use any metal of that. So from the cost perspective, so normally they're going to use the palladium on the carbon. So the surface is going to be palladium, you're going to be the carbon next to that. So palladium is the one that's going to act as catalyst. Okay, so for that, so the metal surface you can see over here, that's the PD surface, right? So you have the metal surface there. You're going to have the orbitals. That orbital is going to be used to absorb hydrogen. So you're going to have the hydrogen molecules there initially, they are bonded, right? You have the H bonding in H2 molecule, right? So now in the metal surface, what's going to happen is individual atoms are going to be bonded. So you don't have the H bond there. So from this H, you're going to have now like this. So you're going to have the hydrogen atom absorbed on the metal surface. So they're going to be easier to transfer into the alkene. Okay? So that's how it's going to lower the energy. So the reaction doesn't have to deal with the breaking the bond between the hydrogen atom. So that's going to cause the higher barrier in the reaction. So now the catalyst does that. You have the broken hydrogen atoms there. So it's going to be easier to add that. Okay? So then those individual atoms are going to be added to double bonded carbon one at a time until all carbons going to be saturated. You don't have any double bond there. Okay, so that's the product. That's the final product. Right? So now you know all the details, like how it's going to happen, why you're going to use the catalyst, right? So change in entropy, enthalpy, everything. But from the exam perspective, just know the reaction and product. Okay? So this one. So you're going to have something like this. So you're going to have the alkene. So let's say ethane, right? It can be any. So H2 and H2. And then you're going to have the hydrogen in presence of palladium, for example. So what is going to be the product? Like this. Right? So now what are you going to do? You're going to add those hydrogens there, right? So you're going to have, so this hydrogen molecule, you're going to add that to the product. So you're going to have the carbon-carbon. So you have two hydrogen already there. So I'm not changing on that. So what I'm going to change is this. So you're going to have the one hydrogen over here, other over here. So that's the ethane, right? So this is saturated. Sometimes we're going to call that saturated hydrocarbon. You do not have any multiple bonds there. All single bonds, all sigma bonds you have. If you have that, that's the saturated molecule. Okay? And the other one, if you have the double bond, for example, that's the unsaturated, right? So you already know that. So this is unsaturated. That's why we calculated the degree of unsaturation, right? Hydrogen index deficiency. We calculate that. So that's the unsaturated molecule. Okay? Good. So this is the summary. So make sure you know this reaction. The whole idea is just to give this. So if you see any alkene, if you add hydrogen with catalyst in it, what's going to be the product? Alkane, right? So alkene to alkane. You're going to have a single bonded carbon with the hydrogen added to it. Right? Easy reaction, right? Alright, any question on that? So now when you see this type of reaction, you can answer it. Right? Okay. So if you don't know the barrier, the exact value of the barrier is going to be something like this. In order of this. So alkene, so both are alkene. And then the alkane, so this is going to be alkane, saturated. And then this is going to be alkene. So the difference energy is going to be something like this. So that's going to be the difference. So before you add hydrogen, you're going to have the energy of the molecule. After you add hydrogen in that, you're going to have the energy, different energy. What will be the difference between that? This is the difference. Okay? Or you can say the difference between the saturated and unsaturated molecule. That's the value. Right? So in principle, you don't need to remember those numbers, but keep in mind that energy of alkane is going to be lower than that of alkene. That's the point. Keep it remember. Okay, so when you compare, so the energy of alkane you have, so this one, that's going to be lower than the energy of alkene. So that's the point. Relatively, right? So if you compare, so always the alkane gonna have lower energy than the alkene, and also alkyne. We're gonna see it next chapter. So alkyne gonna have also higher than alkane. Right? All right. I think that's it for the chapter. So if you have any question, I can answer that. If not, then next chapter, chapter 10. All good? All right. Then, so I'm going to go to chapter 10. Okay. This is now, this is going to be very similar to chapter 9. Right? So why? You know the answer, right? See name over here. So you have the alkyne. So before we had alkene. So this is the difference over here. Right? So before we were saying something like that, carbon-carbon double bond. So now here we're gonna have carbon-carbon triple bond. That's the difference. Or if you see the specific bonding, so you have the 1 sigma and then 1 pi, right? So for alkene, you had a 1 sigma bond, 1 pi bond between the carbon atoms. Okay? So now here in chapter 10, you're going to have the 1 sigma and then you're going to have 2 pi between the carbon atoms. That's the difference. Right? So now you can just use your general concept. So all the reactions in chapter 9 was based on the carbon-carbon pi bond. That's the initiation of reaction, right? That's the reactive center. So whatever you added over there, doesn't matter, water or hydrogen, any electrophile you have. So the pi electron is going to act as nucleophilic center. So you're going to use that to make the bond with electrophile you have, followed by nucleophile you're going to add to the end of the carbon. That's the basis for the whole chapter. So now here you can execute the same thing. So you're going to have one more addition than alkene because you're going to have 2 pi bonds. So for the first reaction, you're going to use 1 pi bond like alkene, followed by, you're going to have another pi bond remaining, right? You're going to have another reaction after that, depending on the conditions you have, until all pi bonds are converted into sigma bonds. Okay? But if you have any control, you're going to prevent that. you're going to have only one pi bond used in the reaction. You can do that too, but it depends on the condition of the reaction. Okay, so that's the whole idea. It's not different, very similar to chapter 9, right? So now you're going to do the electrophilic addition, if you see the title over here. So that's what we have been doing in chapter 9, right? And the redox reaction, in particular oxidation reaction, right? Followed by the reduction reaction. So you're going to do the same reaction over here, right? Going to be very similar. Also going to be, you can take as a review of chapter 9 if you come, right? So now, let's start from the properties and then nomenclature for orbitals, and then we're going to go to reaction after that, right? So properties, solubility in particular, right? What do you think? Going to be soluble or insoluble in water? It's like alkene, right? So you have the pi bond like alkene, hydrocarbon. So it's going to behave like alkene or alkane. So it is normally insoluble in water. In particular, when you have the longer chain of the hydrocarbon, right? And then the other, like a carbon-carbon triple bond. So of course, if you compare with carbon-carbon single, double, triple, which is going to be stronger? Double is going to be more stronger than single, and then triple is going to be the strongest if you compare all these three, right? If you have the linear chain, so they're going to result the stronger intermolecular interactions. So dispersion is the one you have over here, right? So they're going to result slightly higher melting temperature, boiling temperature than alkane and alkene, right? So slightly higher. So another thing you're gonna do is classification. So you're gonna have 3 different types of alkynes, right? So first is terminal, and then the second gonna be the symmetric, and then the third gonna be the asymmetric. You're gonna have 3 types of those compounds, right? So terminal is obvious. So what that means? Means at the end, right? So if you have any triple bond at the end of the chain, so if you see the carbon chain over there, so this is at the end, right? If I number just the carbon, 1, 2, 3, 4, 5, 6. That's what you do when you name that, right? For the nomenclature, you're going to label the carbon atoms. So this is going to be the parent you have, the longest possible chain, right? So where is the triple bond? In the middle or at the end? At the end. And that's why it is stored. Okay. For any molecule, if you have the carbon-carbon triple bond at the end of the molecule or the end of the chain, this is called the terminal alkynes. Okay. And then the number 2, symmetrical. So you know the molecular symmetry before, right? So what that means? You're going to have some plane. If you cut through that, you're going to have the identical pieces over there. You're going to have 2, 3, 4 equal halves, depending on how many plane you have in the symmetry point, right? So the same thing. If you cut through the triple bond in the molecule, you're going to have the 2 pieces. If you have the exact same pieces, that's the symmetrical. Okay. So here let's say I'm gonna cut through this, and then I'm gonna compare the piece on the right to the piece on the left. You have the same number of carbon, right? Same number of hydrogen. You have the same linkages, so you cannot distinguish that. So it is symmetrical. So you're going to be in the middle. So the triple bond is going to be in the middle of the chain. So you're going to have the 2 equal half there. So this is symmetrical. And then the other going to be the unsymmetrical. So now you're going to do the same thing. You're going to cut through the triple bond. So now you're going to have the 2 halves like before, right? But you will not have the identical. You're going to have the different pieces, so you don't have any plane of symmetry there. That means it is unsymmetrical all the time, right? So it's not hard to classify that. So terminal is going to be the one in which you have the triple bond at the end of the chain. And then the symmetrical, you're going to have the triple bond in the middle of the chain. When you cut through that, you're going to have the equal or identical pieces. And then the unsymmetrical is different than that. You're going to cut through the triple bond, but you're going to have different pieces that are not identical. Okay? So that's how you're going to classify. So terminal, symmetrical, unsymmetrical. Alright? So now, the next thing is, you're going to do the redox reaction. So for that, you're going to have the oxidation number calculation. Right? So which is oxidized, which is reduced. You're going to do the exact same thing you did in chapter 9. Okay? So as an example, you have molecule over here, carbon-carbon triple bond. So if you want to know what's going to be the oxidation number of these 3 carbon atoms, so how are you going to calculate it? Right? So what's going to be for the first carbon? Yeah, value for second and third. So can you calculate for the first one? First carbon? First was the left, okay? So what I mean is from the left. So this one. It's easy. You don't have that large number. So what is going to be the oxidation number for the carbon, the first carbon from the left? 0. So you're going to have the 4 valence electron. And then how many electrons it's going to own in the molecule? So
7, right?
you have the same carbon atom, so you're going to have 2 electrons over here. You're going to do half for that, right? So you're going to have 1 electron from the carbon-carbon bond. And then 2 from the CH bond, because carbon is more electronegative. Remember that? So 1 plus 2, 3, plus 2, 5, plus 2, 7. 7. So you're going to have minus 3, not 0.
Very good.
Right? So you can have 0. Let's say you have this molecule. So you're going to have CH3. Let's say CH3. Let's say CH3 over here. CH3 over here. So now if I ask, what's going to be the oxidation state of that carbon? Now it is it. Okay? So you have the carbon-carbon bond, so you're going to make the half for each bond you have. So you're going to have the 4 valence 4 actually it's gonna own, so you're gonna have the 0. So it depends on molecule, right? The same formula. So carbon is in valence electron going to be 4, right? So they're going to be there always 4 minus, you're going to count the electrons. So remember the neighboring atom to the carbon. If it is less electronegative, both the bonded electrons going to go to the carbon. If it is same as carbon, which is carbon, then you're going to do a half-half. If it is more electronegative than carbon, say for example COH, right? Let's say you're going to have COH over here. So for this bond, what are you going to do? Both electrons going to bond on the oxygen, are going to put on the oxygen. So carbon has 0 from this bond. It doesn't gain or own anything from that bond, right? So that's how you're going to do. So when you split electrons to own it, then you're going to have 3 cases. Same electronegativity, half-half. Less electronegative than carbon, both carbon are going to be on the carbon. More electronegative than carbon, then carbon going to have no electron from that bond. Remember that, right? This is exactly same as chapter 9. So that's how you're going to do. So now you can calculate for the second carbon, right? You do the same thing. So for the second, you're going to have 4 balance, and then you're going to have the 1, 2, 3 from there, and then 1 from the other side. So it has the carbon on both sides, so half-half, right? So 4, and then you're going to be 0, right? What about the other one, the third one? So the third one is going to have 4 balance. So now you have the 3 from the carbon-carbon triple bond, half-half, and then both going to be for the carbon from the CH. So 3 plus 2 going to be 5. So you're going to do 5. So you're going to be minus 1. Right? So that's how you're going to calculate. So again, this is kind of a repeat of chapter 9. So now you can also do the hydrogen deficiency or the degree of unsaturation for the alkyne, right? Remember you have the formula. So you can use the same formula that you can calculate. Okay? It is same as alkene. So now, the next thing going to be the nomenclature. How to name this. So now for every chapter, nomenclature is going to be kind of like a repetition, the same thing. It's not different, right? If you recall the first nomenclature of alkane, you're going to do the same thing. Essentially, the first few basic rules going to be the same. You don't have any change on that. So, number 1, you're going to find the parent chain for all type of molecules, right? Number 2, you're going to number the carbon atoms. You're going to label that in such a way that, so now you have the condition over there. What type of groups there, right? And then you're going to see the substituents on that and put everything together. That's going to be the name. So you're going to do the same thing over here, right? So let's see. You have the molecule over here. So you're going to choose the parent chain for that. So going to be the longest possible, right? So you cannot choose the short part of the molecules with the least number of carbon. You're going to have the maximum number of carbons possible for the chain. That's how you're going to choose the parent. Okay? And since it is triple bond, the condition is both carbons you have, the triple bond, should be the part of the parent. You cannot put this as a substituent. Okay? You have the same condition in chapter 9, right? So you have the both double bonded carbon as a part of the parent chain. So you will do the exact same thing over here. You have triple bond over here, you're going to do the same thing. Two carbon atoms that have the triple bond must be the part of the parent chain. Okay? So that's the reason why you're going to do this. So you have one carbon there, two carbon, 3, 4, 5, 6, 7, 8. If you go this route, you're going to have the 8 carbons on the parent chain. If you choose from any other side, you're going to have less than that number. Okay, so that's the reason why we're going to choose this, because it has the maximum possible carbon in the chain, and also the two atoms that have the triple bond on the sequence, on the parent chain. Okay, so now you know the parent there. So now you may be thinking, why we're going to write number? We're going to start number from the right, not from the left. Can I do from the left, like this one? So 1, 2, 3, 4, 5, 6, 7, 8. I can have the same carbon numbers, right? So when you number from the left, you're going to give one label for the triple bonded carbon. When you do it from the right, you're going to have another label for the triple bonded carbon. So which one is going to be right? Again, this is not different. So this is for all, exactly as alkene, right? So as far as possible, you're going to have the lowest label possible for the triple bonded carbon. You have the same criteria for alkene, right? You do the same thing for double bonded carbon. So that's why we're going to go from the right all the way to the left. So you're going to have the number 2 on the triple bonded carbon. Okay? So that's the labeling. And then now we're going to go to the substituent after that. So the parent is fixed. So now you choose the parent chain, you label the carbon atoms so that the triple bonded carbons have the lowest possible number in it. So it is done. So now you're going to go to the branch after that. Okay? So what's going to be the branch? You have this branch over here. You have this branch over here. 2 substituents, right? So one is just the linear. We have the linear carbon, 2 carbon attached to the parent chain, right? So you have like something like this, carbon, carbon, and then this is attached to the parent you have, right? So that's what you have. So what is going to be the name for the 2 carbon? Ethyl, right? So if you see the table, long before in the alkane chapter, you're going to have the long table over there, right? So number of carbon you have, and the name for that, the base. So ethyl is going to be the name of that. Okay? And then the other one is going to be, how many carbon you have? 1, 2, 3. You have the 3 carbon chain that is attached to the parent. So what is going to be the name for 3 carbon? Propyl, right? So if you had the attachment at the end like ethyl there, you're just going to write propyl. you have the joining in the middle carbon instead of the terminal carbon there. When you have the middle carbon, we're going to call the iso. Okay, so isopropyl. That's why you're going to write name for that. Right? So now the branching is fixed. Isopropyl, ethyl. We have the two names for the two branches. You have all the parent and everything labeling good. So now you're going to put all together. Right? So you're going to have the 8, right? So it's going to be octane. So you have the ANE, so you're going to change that to Y, right? So triple bond going to be Y. So you're going to say the octane. So YNE for that. Oct 2YNE. So you have the second carbon with the triple bond. So oct 2YNE. Or you can write 2 oct YNE. Same thing. You can write either way. Okay. So that's going to be for the parent. So now you're going to put the ethyl. That's on the fourth carbon, right? So 4 ethyl. And then the 5 or 6? 5, right? So 5 isopropyl. And then 2 octane. That's the name. To put everything there. Good? So this should be clear, right? This kind of revision. You're going to do the same thing for all molecules. They stay the same. Choose the parent chain, number it or label it, see the substituent in it, and then you're going to put all together. Okay? Again, the alphabetical order, if you have like a different substituents over there, you're going to follow that. So now, since we went through alkene and alkyne, so we have two different already covered, right? So how are you going to name if you have both in the molecule, right? So like something like this one. So you have the double bond, you have the triple bond, right? You have the triple, you have the double. Both on the same molecule. So the basic steps are same. You're going to do the same thing. So you're going to choose the parent chain so that both double and triple going to be on the parent chain. You're going to choose like that, right? And then what are you going to do? You're going to number the carbon atoms. You're going to label that. And then see the branching after that. And put all things together and do the same thing, right? But the order is this. If you have many functional groups over there, so this is going to be the order. So you're going to see this table all the way you complete OChem 2. The same table. Going to be the same order. Okay? So in OChem 2, we're going to deal with the carboxylic acid, amides, aldehydes, ketones, all those functional groups. We're going to cover all. So one group going to be in one chapter. So you're going to deal all the functional groups. And then when you name, you're going to do the same way. Right? So basic points going to be the same. If you have the multiple functional groups, then the table priority you're going to use. So the carboxylic acid is going to be number 1 priority. And then you're going to go all the way to the down. So far, we just covered these, right? So both alkene and alkyne going to have the similar priority, equal priority. When you have both, so what we're going to do is, we're going to write the double bond followed by the triple bond in the parent chain. Okay? So En going to be the position for the double bonded carbon. Yn going to be for the triple bonded. So both going to be the part of parent chain. and then you're gonna name as before. Okay, so let's see the first one. So I'm gonna do 1, 2, 3, 4, 5, 6, 7, 8. Right? So that's the number in the parent. So why I did from the right, not from the left? So remember, the double or triple must have the lowest possible numbering in the parent chain. If I do from the left, the triple bond going to have the last labeling. I don't want to do that. Even if you have the same number or similar number for the double bond. So for both. Okay. So that's why I went from the right to the left. So number 1 is going to be for the triple bonded carbon. Right? So now 8. So you're going to have the oct, the base name for 8 carbon. So I'm going to write oct. This is part of the parent, right? So this is parent you have. So oct, in, and YNE. You have both there. So oct is going to be the base, and then you're going to write the in after that. You're going to write the YN after that, and then you're going to write the position. So 1 for the triple, 5 for the double. So I have the number 5 for the double bonded carbon. So 5 in, and then 1 YN. So this is part of the parent. Okay. So now the substituent, you have only 1, right? So methyl. So where is going to be the methyl? 3. So you're going to have the 3 methyl. So this is going to be the bronze, right? So you have the 3 methyl bronze and then the parent. Okay. And then you have one thing over here. Sometimes you have that, sometimes not. We're going to ignore that. So E over here. So why you have the E over there, This one. So why is that? Sometimes you're going to have R and S, right? So why you write E over there? Why not Z, for example? So you have the double bond, right? So you're going to focus on that. So double bonded hydrocarbon going to have G or E isomer if you have more than 2 substituents. If you have only 2, what are you going to do? Cis and trans. If you have more than 2, you're going to call E and G, right? So here, so you're going to have 1 over here to the 7 carbon, and then you're going to have the 8, this way. So this is 1 substituent for this carbon. You have the hydrogen over here, it's not shown. And then to the other side, you're going to have the hydrogen over here, and then the different color to make easy to read. So all things over here are going to write as R, right? You have the R over here. Okay? So you have on the different side of the double bond. That's why it is E. If you are on the same side, it's going to be G, right? So that's how it is. Alright, already 50. Alright, we're going to stop over here.